All right. So let's look at logs and exponentials. They are how are they related? How is logs related with exponents? It's the inverse, okay? It's the inverse. Log and an exponential function. So the inverse of a log is 10 power x. So here, look at this. An exponential function is something that looks like this, 10 to the power of x. An exponential function always goes through, the parent function anyways, goes through the y-intercept of 1, and then there's an horizontal asymptote on the x-axis. That is an exponential function. A log function is that function's inverse. Now remember, inverse is something graphically, inverse is something that's reflected on the y equals x line. Algebraically, it's when x becomes y and y becomes x. But graphically, an inverse is something that is reflected on the y equals x line. So this function y equals 10 power x, the inverse would look like this. Imagine there's a mirror on this red line. It would go this way. Instead of going through the y-intercept of 1, it goes through the x-intercept of 1. And that is the function log x, or log base 10 of x. That base 10 is invisible, so we just write it as log x. On the other side, on a calculator, there's the ln button. Ln stands for the natural logarithm. Ln is the inverse of e to the power of x. So e to the power of x would look something like this. When you flip that on the x-axis, you would get something like this. So that's where ln comes from. That's the logarithm of the natural number e to the power of x. And look at the notation, log notation. You can have something like this. 3 to the power of x is equals to 9. What's the value of x? If 3x is 9, what would be x?
It's 2.
It's 2. So now this, let me just see how the book calls this. Does it use ABC? I'm going to use this format. Log base b of c equals a. And that would be b power a equals to c. All right. So this is the format. If you have a base to the power of a number, and that's equals to something, this is in the exponential department. As a log, you can rewrite that expression in this format. So this thing, when you rewrite it as a log, okay, look at this. The base 3 becomes the base, it becomes a subscript. So log of base 3, and then your 9 is here, and that's equals to x. And we know here the x value is 2. So that's how you go back and forth between log and exponential. And you need to understand this, because to solve any log equations, you need to know how to switch between the two forms. So maybe using that idea, let's see if we can evaluate some of these answers. So the our goal is to find what is this entire expression equals to. Like how log 39 is equals to 2. What is that entire thing equals to? Now, the way to solve this is by setting it up. So let's assume that the answer to this is x. Right now, we're in the log notation. I want to write it in an exponential notation. If I want it in this form, what does this become? Right now, it's in this form. I want to go back into this form. So your base is 4, right? See B? That becomes 4 on the outside. It's no longer a base. To the power of a. A is whatever is on the other side of the equation. So other side of the equation, we have an x, right? B power a, and that's equals to c. C is this number here. So this becomes 4 power x equals 64. 4 power x equals 4 power 3. X is equals to 3. So that entire thing is equals to 3. Did that make sense?
Mm-hmm.
Let's set up the second one. How would you set up the second one there? What power what equals what for the next question there? You can set it equals to x.
2 to the power of x equals -4.
Yes. Can we evaluate this? Now think about this graphically. What does 2 to the power of x looks like? It looks like a generic exponential function. 2 to the power of x looks like this. Just for practice, I'll show you what 3 to the power of x looks like. 3 to the power of x is gonna look like this. At an x value of 2, the y value is 4, the y value is 9. So that's 3 power x. Like 100 to the power of x would come from down here, go through the y value of 1, and then spike completely. That would be 100 to the power of x. Anyways, those are not important. What's important here is 2 power x. Now think about this. That's the graph of 2 power x. Would the y value for this curve ever be -4? Is there any value of x for which the y value for this graph is -4? Is that possible?
No,
No, it's not. So can we evaluate that expression? 2 power x equals -4.
we can't.
We cannot. That's right. So that's it. You're done there. Okay? Because it's not in the domain. It's not in the domain. Let me show you something. So for us, it's not doable, right? But what if we were on the complex number system, on the imaginary number system? Right now we're on the real number systems. You can't take the square root of a negative number. But let's look at it from the complex number system, which is a grade 12 concept, or if you have AP class or gifted classes, you can see this from grade 11. So the idea behind complex numbers is this. There's one simple concept. Square root of -1, yes, we know. This, you can't evaluate it. But square root of -1 is defined in the complex number as the imaginary constant I. So this one, what you can do is 2 power x is, no, that doesn't really work here, does it? Because are we taking a square root? We're not taking the square root. We're taking the log inverse. All right, here's what I was trying to say. I'm trying to evaluate this for x. To evaluate this for x, what you need to do is you need to take the logs on both sides to kill the 2. So you take log 2 to the x equals log of -4. Now, log of base 2 cancels with itself. because they're inverse functions. Log of base 2 is the inverse function of exponentials, so they cancel each other out. So on the left-hand side of this equation, we have x. On the right-hand side of this equation, we have log base 2, negative 4. Now let's look at the curve of log base 2 of x. Log base 2 of x looks like this. Log base 2 of x. Would the x value for this log function ever be negative? We want to find what's the y value for this curve. Again, look at the curve. It starts at the x-axis because there's an asymptote here. Can this curve ever be negative 4? Can the x value for that curve ever be negative 4? No, right?
No.
So that means this cannot be evaluated, okay? But
Mhm.
here's where I was going with the negative 4. It doesn't apply to exponentials, but it would apply to this one. It doesn't apply to here because you're not taking the square root of a negative number. So here, when you take the square root at this level, the square root of anything is plus minus. This is what I was trying to tell you. I in the complex number system is negative 1. So what you do with this is you replace this with negative 1 times a 4. So it becomes plus minus negative 1 times root 4. Root 4 is 2 plus minus, and this is I. So you can actually evaluate negative roots if you're on the complex number system. Obviously, it doesn't apply to us at this level, but depending on your teacher, if your teacher wants to have some fun, then they might introduce this concept. Yeah, let's see what else we can do. Once you understand that, the main idea behind logarithms is solving exponential equations. To do that, you need to understand the laws of logs, all right? So let's start with exponential laws, and then we will do log laws. So exponential logs, there's one for addition, there's one for subtraction, and there's one for power. If you have a power b times a power c, what does that equals to? What do we do with the exponents? For example, if you have 2 power 3 times 2 power 4, what does that equals to?
7.
Yes, you add the exponents, right?
Mm-hmm.
What if it's division? What do you do with the exponents?
You
You
subtract.
you subtract them. What if it's like this? What if it's a power, a power b to the power c? What happens there?
You multiply.
You multiply. So those are the exponential laws. Now the same thing exists for log. So if you have log of AB, okay, they're being multiplied. What you can do is you can split them into an addition, like that. If you have a division, you subtract them. And if there's a power, log of a power k, you can bring this power down, okay? So those are the log laws. So using this, we're going to solve some problems. It's not that bad. It's quite fun when it works out. Doesn't always work out. All right, so let's start with A. So you have log base 3 for both of them, right? You can combine them. How do you combine them? You're going to use the product law. Right now, you're on this side of the equation. What do we do with the two numbers inside? Multiply, divide, or what? They're being added, right? You're going to use the product law. You're going to multiply them together. So before you had two logs, now you only have one log. Yeah?
Mhm.
So then it becomes log 3 of 27. Now remember what that means. That means there exists a number. 3 to the power of some number is 27. The answer to this is going to be this number. 3 power what is 27?
3.
3. So log base of 27, this entire thing evaluates to a 3. And you're done. B. We have a minus. We're gonna divide them. So log base 2 of 48 divided by 3. That's log base 2 of 16. Now you ask yourself, 2 to the power of what is 16? What is the number? 2 to the power of what is 16? 4. Okay, 4. 2 power 3 is 8. 2 power 4 is 16. 2 power 5 is 32. Yeah?
Mm-hmm.
So the answer is 4. Okay, what about C? What do we do with C? Which law would work for C?
The power law.
Okay, so what does that equal to? So here, look at this. Log base of 5, it needs to be to the power of. The cube root of 25, if I want to write that as a power, what is that equivalent to? 25 to the power of what?
Or 3.
1/3. So then you can bring the 1/3 outside using the power rule. What's log base 5 of 25 equals to? So log base 5 of 25. So again, you want to think of this exponentially, right? So there exists some number x where this equation becomes true. What is x?
2.
2. So log base 5 of 25 is 2, and the 1/3 comes outside using the power rule. Therefore, the final answer is 2/3, and you're done. Cool?
Mm-hmm.
Is this difficult?
No.
Okay, here it says simplify, clean it up. Okay, let's look at A. How do we clean this up? Gonna use the power rule first, like that. Bring the 3 out. And now you're asking yourself, 25 to the power of something is 5, right? Look at this. 25 to the power of something is a 5. How do we solve this equation for x? To solve an exponential equation means the unknown is in the exponent. The way to solve it is there's two ways. Either you take logs on both sides, that's the harder way, and that's the last resort, taking logs on both sides. The easier way is making sure both sides of the equation has the same base. So on the right side of the equation, the base is 5. So now we want to ask ourselves, is there a way to turn the 25 on the left to a base 5? Yes, there is, right? 25 is 5 power 2. Does this help? What's x equals to?
Over 2.
1 over 2, yes. So log base of 25 of 5, okay? That entire thing was x. So that entire thing is 1 over 2. So this becomes 3 times 1 over 2, 3 over 2. Cool?
Mm-hmm.
It's not that difficult. Okay, let's look at b. Yeah, how would you do b? We need to clean this up. So the final answer would probably be one number with no logs or anything. So which law would you use here? Power,
The
what was it?
power law.
The power law you want to use? Let me see. Okay, yeah, sure, let's do it. So if you use the power law, what happens? What comes outside? So look at this. The power here is 1 over 2. I can even write it like this, log 236 to the 1 over 2. Are you joining from a different thing? So 36 to the power of 1 over 2 minus log base 2 of 72 to the power of 1 over 2. Now let's use the power rule. That would allow us to bring the 1/2s outside. Now what? Because 2, there's nothing, 2 power nothing is 36, so that's not going to help us. This right now, you can't evaluate it, so you need to do something else. So what you do is you want to use the quotient rule or the division rule. You want to find a way to combine these two logs. What I'm going to do is I'm going to take 1 over 2 common. That leaves me with log base 236 minus log base 272. And what do we know? Log A minus log B. If the bases are the same, here the base is 2. That is log A over B. So I'm going to use the quotient rule to combine these. So it becomes 1 over 2 times log base 2 of 36 over 72, or 1 over 2. So now we have this equation. Log base 2 of 1 over 2 is x. In other words, 2 to the power of x is 1 over 2. If 2 to the power of x is 1 over 2, what is x equals to? Two to the power of x is 1 over 2. What's x equals to? It will be negative 1 over 2. because 1 over 2, what you can do is you can take this 2 in the denominator, you can move it to the numerator, right? When you move something from denominator, numerator, numerator, denominator, the sign of the exponent flips. Right now, there's an invisible 1 as an exponent. So when we take this to the numerator, it becomes 2 power x equals 2 power negative 1. And we want to take it to the numerator because to solve an exponential equation, if you don't want to use logs, you want to make sure the bases are the same. So this is means x equals negative 1. So this entire thing is negative 1. So the answer, final answer, is going to be negative 1 over 2. And you're done.
Hmm.
It's not that difficult. You just have to think about it in terms of which rule you want to use. Let's look at this one. So this one is the other way around. This one, they've already cleaned it for us. Now our goal is to rewrite this as 3 different exponents. One with z, one with x, and one with y. So basically unsimplify this or write it as 3 individual logarithms instead of one combined one. Alrighty, so we have to split this apart. So the first thing I'm going to do is I'm going to notice that this is the numerator, this is the denominator. So I'm going to use the quotient rule, which says log of a over b is equals to log a minus log b, as long as the bases are the same. So here the base is base b, so we're good. So this becomes log of base b numerator minus log of base b denominator. Cool. But we need to have one log for each variable. Right now, this is combined. How do we split this? I'm going to use the product rule, which says log of AB is log A plus log B, right? So now look at this. Log base B of Z unchanged minus, now this part becomes log base B of X plus log base B of Y. There is one mistake in this line. What's the mistake? What did I do wrong? It has something to do with the signs. Whenever you're dealing with a term that has a minus sign, like this, make sure when you're doing one-to-one conversions, make sure you put a bracket around it. Okay?
Hmm.
Whenever you're dealing with a minus sign, make sure you put brackets around it. If you don't want to put brackets, if you see it, then you see it. This is going to be a minus sign. That was a mistake. That was not a mistake. That was on purpose. That was more of a pop quiz. Okay, are we done? I think we're done. That's it. Final answer. We've written as 3 independent logs. Okay, what about this one? Same question. We want to write it as 3 independent logs. What would be the first step?
The power rule.
The power rule. Can we do this in one step? Let's not do it in one. Let's do it in step by step. So 1 over 2. You understand that, right?
Hmm.
The root comes outside because that is equivalent to this power 1 over 2. Square root means the power of 1 over 2. All right, what's the next step?
The product rule.
The product rule. Now look at this. 1 over 2, bracket open. There's going to be 3 logs. Look at x power 5. I'm going to do this in one step. It'll be 5 times log bx plus y doesn't have an exponent. Z does. That 3 will come outside. and you're done. It's that easy. And I guess you could throw the 1 over 2 in there, so this becomes this. And that would be the final answer. Cool? Two
Mm-hmm.
steps, not that difficult. What about this one? Which rule? Product. Plus means product rule. Log base 5, 3 times 1 over 3. Log base 5 of a 1. Now remember what that means. That means 5 to the power of x is 1. What's x?
0.
0. And that's the proof, okay? Start here, get the 0, and say that's on the right side, and you're done. Again, not that difficult once you know your rules. Let's look at this one. So for this one, we want one final answer. It's going to evaluate to a number. Probably have to use all three. All right. How do you evaluate this log? What would be the first step? What would you do?
The quotient rule.
You want to break it down? All right. So log, like that.
Mm-hmm.
Okay. What's the next step? So the next step would be for this one, you want to use the power rule. And let me know if you don't understand where the 1/5 comes from. For this one, you can't really do anything. What's log base 3 of 27? 3 power something is 27. What is it?
3.
Yes. Minus 3 power 4 is 81. 5 is 323. Okay, so 7 maybe. 7. So this is 7. 3 power 7 is that. So you have 3/5 minus 7. 3/5 minus 35/5, right? 7 times 5, 35. So negative 32 over 5 is the final answer. And you're done. Let's look at this. Let's solve some equations. So this is the equation that we're given. The unknown is here. The unknown is the letter h in the exponent. How do we solve this equation for h? What would be the first step? No? Okay, here's what you do. You want to get rid of the 200. When you're solving an exponential equation, remember this is the idea, right? You want to be in this form. You want to be in the form where ideally the two bases are the same. You'll see that this is not always going to be the case. If the two bases are not the same, like this, then you have to use logs because there is no way to write 2 in terms of 3 or vice versa. But here, you can write 9 in terms of 3, so no logs here. No logs, logs on both sides. And that is how you solve an exponential equation. There's only two ways, really. It depends on the base. If you can write it as the base, no logs. If you can't write it as the base, logs. So step number one, basically you want to get rid of everything except the term with an exponent on one side of the equation. So step number one, divide both sides by 200. When I do that, look at this. I get 116. Can we write 116 in terms of 1 power, oh, sorry, 1 over 2 to the power of something? So what I'm asking is, can we write this? 1 over 2 to the power of something is 1/16. What is it? Power 4. Remember how exponent power works? 1 power 4 is 1. 2 power 4
Mm-hmm.
goes in the denominator, 16. So 1/16, you can write that as 1 over 2 to the power of 4. If you couldn't, you would use logs, not the end of the world. So this one becomes 1 over 2 to the power of 4 equals 16, sorry, equals 1 over 2 to the 16 over h. All right, what's the next step? Does anything cancel out? Yes, the 1 over 2's. You see this?
Mm-hmm.
This is the same thing as 2 power 3 equals 2 power x. X is 3 because the 2 cancels out. Same idea. This is gone with this. What you're technically doing is you're raising both sides of the equation to the 2 power. This is what you're doing. 2
Mm-hmm.
power 1 over 2 cancels with each other. So anyways, the main point here is that the bases, if they are the same, they disappear. So therefore h is 4 and you're done.
Mm-hmm.
So that was an example of an easy exponential equation where you can write the base in terms of the other. That's not always going to be the case though. Let's look at this. What type of an equation do we have? Exponential equations. How do you solve exponential equations? Two ways. Either you take logs on both sides or you make sure both sides have the same base. Okay?
Mm-hmm.
What would you do with this? I'll give you a hint. You have to take something in common. The only way to solve this is if you take something in common. See, there's a 2 power x here. There's a 2 power x here. You want to pull that out. Okay, that's the idea. How do we pull that out though? To pull a 2 power x, you need to break down this. Remember the first exponential rule, right? The product rule of exponents. You want to undo that. So 2 power x plus 2 is 2 power x times what? Talking about this rule. Uh, Remember that? That's the first exponential rule. So 2 power x plus 2 is 2 power x times 2 power 2. Do you agree?
Mm-hmm.
Why are we doing this? Is because we want to take the 2 power x in common.
Uh-huh.
What's the next step? Pull out the 2 power x's. If you pull out 2 power x, what are you left with inside the bracket?
2 power 2 minus 1.
Perfect. This is 3. Do you agree? 4 minus 1.
Mm-hmm.
And this is 8. So what's x?
It's 3.
3. Done. Easy peasy. So the hardest thing here was this. From here, it's grade 10. You also got this one. It's probably gonna be, this is a hard question. Okay, the last one was easy. I'm fair. I like to think of myself as fair. I will tell you when the question is hard. Not everything is gonna be easy. This is an example of a hard question because one method of solving an exponential question doesn't work here. There is no way to write 2 in terms of 3 or 3 in terms of 2 power something. There's no exact value you can give. So you have to use logs. Okay, that's the way to solve this. There's two ways. Either, I don't know which one's better. I'm going to show you both ways. You have to use logs, okay? Keep that in mind. There's no other way to do it. You have to use logs. Now the question becomes, do you use logs in the beginning or do you clean it up and then use logs? So I'll show you both ways. So let me show you clean and then log, and then we'll do here just purely log from the first step. So here from the very first step, we're going to log it. 2 power x plus 1 equals 3, sorry, log of 3 power x minus 1. On this side, though, we're going to do what we did in the last question. We're going to split it apart. And you can be the judge of which method you prefer. So when you do this method, you want to use the power rule. So this becomes x plus 1 times log base 2 equals x minus 1 times log base 3. When you do it this way, um, 3 to the power of negative 1 is 1 over 3. I'm just going to rewrite this as 1 over 3. When you do it this way, you want to make sure all the x's are on the same side of the equation. All the numbers are on the same side of the equation. So this becomes 2 power x over 3 power x equals 1 over 6. You with me so far?
Mm-hmm.
Then what you want to do on this side, you have to take x as common, which is more difficult than it sounds because to take the x as common, there's an x here, there's an x here. Somehow both of these x's have to be on the same side of the equation. The only way to do that is by opening that bracket. So this becomes x times log 2 plus log 2 equals x times log 3 minus log 3. Now I'm going to move the x's to this side. I want to move the logs to the other side. X log 2 minus x log 3 is equals to negative log 2 minus negative or minus log 3. And then for the final step, you want to pull an x out like that. And then you want to divide both sides by that. And there you go. That's the exact answer using that method. If you plug it in a calculator, it'll give you an irrational number. So usually they want the answer to be in exact form. So that's the final answer using that method. Let's see if it's easier or harder using the other method. I reckon it's easier because here what you can do is you can combine this into 1x like that. And then you take logs on both sides. I'm going to skip a step. And then therefore x will be log of 1 over 6 divided by log of 2 over 3. And somehow this number, if you plug it into a calculator, you can do that on the side. And this number, they're equivalent. Which method is easier? Definitely this. This one, there's more room for error. But ultimately, it doesn't really matter because the answer will be the same. And this is an example of a hard exponential equation question. It is going to be harder simply because you can't have the same base on both sides of the equation, and then you can cancel that base out. So keep in mind for that type of equations. Let's do one more for the day, one more for the ride home. This one. Yeah, when you see this question, do you think we need to take logs on both sides, or can we probably do this by changing everything to base threes? What do you think? If you can change everything to the same base, you don't have to take logs, okay? It makes things easier, so let's do that. 81 is 3 power 4, 27 is 3 power 3, 9 is 3 power 2, right? Like that.
Mm-hmm.
This becomes 3 power 4x plus 4. And again, remember, when you're multiplying something, you're adding them. Actually, this question was way easier than I thought it would be. And that's usually the case, simply because when you have the same bases, you can cancel out the bases. This is very powerful. It's much more efficient. So the answer here is what? X equals 0. And you're done. Cool?
Mm-hmm.
All right, let's call it there for today. I'll see you next time.
Okay, thank you.
Bye bye.